Hey, good afternoon, guys. We are almost done. Yeah. And what we learned now can be applied to many places. This is just the basics. Remember that. Yeah. And in real life, things are more complicated because materials we studied here was linear, elastic. In reality, materials are not linear; they are non-linear. They are not elastic, perfectly elastic. They are viscoelastic, plastic, you name it. Geometry also, we assume that theta is small, u is small. In real life, it's not like that. Yeah? Small means how much is small. So for beam bending also, for example, if you apply load, there will be quite some displacement, right? So although we have assumed this to be very small quantity, based on that even the solid mechanics is based. But you have to study more and more to realize that things are even more complicated. But the thing is, if you can't solve a simple problem, you probably can't solve the difficult problem. So this is where you start. Yeah, rest becomes nonlinear elasticity, and all those are different forces that you have to study. And their simple one inversion of matrix doesn't work. There it will be, you have to apply the Newton-Raphson method, if you remember, numerical analysis, right? So this is non-linear equations you have to solve now. There it is a linear equation. That's why linear. There it is non-linear equations. Hence Newton-Raphson and all. Right? You have to solve. Okay. So basically the last chapter that we had studied was on beams, and so far we found out the shape functions. So we call it beta 1, this is 2, 3 and 4. Corresponding to that, we find out in 1 x. We found out this as, what is the value, guys? 4 over L cube.
1 upon L cube.
1.
X minus L square.
X minus L.
2 square. 2x plus L. 2x plus L.
Yeah. So you can see that when we put the x equal to 0, then we automatically get 1 in the square from here and here. For all others, this becomes c. So what we see in this case is n1 x equal to 0 equal to 1, n1 x equal to L is 0, and then dn1 over dx at x equal to 0 is equal to dn1 over dx. X equal to L, both equal to 0. Yeah. Similarly, we can find out what is the value of, what is expression for n2, right? And n2x equal to 1. Now we have to find out what is the property of n2. n2 is a cubic, as we know already. Right? uy is a cubic function. Right? This is alpha, as said, x plus gamma x square plus delta x cube. So you have, so, and x is a function of n1, n2, n3, n4. So this cubic nature comes from these 4 shape functions, and hence this is also cubic. And you can guess now, n2 corresponds to degree of freedom number 2. That means what? That really means that n2 x equal to 0 will be equal to n2 x equal to L is equal to. Okay. Now dn2 dx x equal to 0 is equal to, and dn2 over dx x equal to L
0.
is equal. So what we see that at x equal to L, n2 has a double root, and hence you write n2 x is equal to x minus L square of it. It's the double zero, right? It has double root. X equal to L is the double root, meaning that this is root of n2 and also root of derivative of n2 with respect to x. Right? Both of them has a root x equal to L. Okay. Now, that's why you have x minus L square of it, and then n2 at x equal to 0 is also 0. Right? So you must have x here. Right? That's it. You got it. And you say this is equal to C1, some constant C1. Okay. Now this we have to impose. So dn2 over dx is equal to C1 x minus L square plus C1x times 2 x minus L. So dn2 over dx x equal to 0 is equal to, this term will be 0, only this term will have, so 0 minus L square equal to C1 L square is equal to 1. So we get C1 equal to 1 over L square. And hence you have n2x is equal to x over L square x minus L. And equal to. n3x. What is the property? n3x equal to 0 is equal to dn3 over dx. That is equal to 0 is also 0. n3 as L is equal to 1. dn3 x at x equal to L is equal to. So this has double root at x equal to 0. Hence, we can write based on this, we can propose n3x is equal to, it will have x square. Right? Correct? No, this is derivative. It's a derivative, no? So x minus L you cannot multiply. We don't know what it is. But what we know is n3 is a cubic. Right? So what we can have is, we just say C2 multiplied by, you can say x plus C3. So this makes it cube. X minus 1, there is no one thing. L, x equal to, you cannot, no. This is derivative, and this one is without derivative. So this will not appear. This will appear. So n3L equal to 1. n3L equal to 1. So if you put x equal to 1, then this equal to 1. Value, this is the value. It's not the root. 1 is not the root. 1 is the value of the expression. Value of n3. Right? This is how we did for N1 as well. Or now you can put these values. So what we get? First of all, from here we get N3L is equal to C2L square L plus C3 is equal to 1. Yeah. So or you get C2LQ plus C2 C3L square equal to 1. Okay. C2LQ. So we get one equation. Second is this, and dn3 over dx is equal to c2 to x multiplied by x plus c3 plus c2 x square. Right? All right. Or dn3 dx at x equal to l is equal to 0. So you have c2. So here we put all the values to c2 l plus c3 plus c2 l square, right? And
C3 from here. We can cancel C2 and L, and then we have L plus C3 from here.
sure, yeah. So from here you can find out c3 plus l or l plus c3 equal to 1 over c2 l square, right? So this whole thing is equal to 0. So we can say or 2 c2l, and then you have l plus c3 is equal to 1 over c2l square, right? So this one plus you have c2 l square equal to 0. Right? Or C2 cancels out, L also. So you have 2 over L plus C2 L square equal to 0. Okay? Or C2 equal to minus 2 over L, 1 over L square, minus 2 over L cube. Right? Okay, so what is C3? C3 is equal to minus L plus 1 over C2. So minus only 1 over C2 is becomes minus LQ over 2 and divided by L square. Right? Okay. And that becomes this is equal to minus L minus L over 2. L over 2. So minus 3 L over. So basically from these C2 and C3, so that tells us that N3x is equal to C2, which is equal to minus 2 over L cube x square x plus C3. X minus 3 L over 2. Last one, N4. And what we know? N4, 0 is equal to
0.
N4 dx at x equal to 0 is also equal to 0. Then you have N4 at L is equal to 0. And N4 over dx at x equal to L is equal to. So yes. Okay, so then N4 x will be equal to, this is double root here, so of course you will be have x square here,
X minus L.
and then also the root at L also, so x minus L as well. And then let's say this is
C4.
C4, then we solve it. How we solve it? That we make that is equal to 1, so Dn4 over dx is equal to C4
To X minus L.
2x x minus L plus C4 x square. Right? Okay, and then dn4 over dx at x equal to L is equal to
C4 L.
C4 L square is equal to 1, so C4 is equal to 1 over L square. Simply n4 x is equal to 1 to x square over L square x minus. So you got the shape functions. Next thing is just the you do the usual stuff. Okay. Now you know that uyx equal to, how did you write? n1x uy1 plus n2x y1 plus n3x uy2 plus n4x. And this one is the trial function, right? We call it trial function. And you have to put that in the big form, right? And what is the big form? Big form was 0 to L, then you have d square w over dx square I, right? Then d square uy over dx square. This is left hand side, and right hand side you have
W.
because these you have.
W.
here the Wx here,
Vx.
Vx.
0 to 8.
Or you can write differently. You can also write, this is the how we do it, but you can also write WL D and L plus,
Minus.
not minus, plus. This will be a plus because sign is different, right? So minus, here the minus that cancels out, makes it plus. So we here W0 at the D0, and so on. Yeah. Then dw over dx at x equal to L times, what is the value here? M at L plus. Yeah. Then dw over dx at x equal to 0 times M at 0. Again, you have to be careful with it. So, see, if you have your, this is the degree of freedom we write, right? So we write like this. This is u y1, u y2, and then you have anticlockwise here. Here also this is anticlockwise. This is theta1 you call it. This is theta2 you call it.
So, this one is negative, right?
This one will be negative.
Okay. Which is sign positive.
Okay, what is the meaning of that? This is the meaning of actual forces that is acting there. So if the force here is acting, say like anti-clockwise, you have to take positive. If the force here is clockwise, then you have to take negative. Right? So there are in two sense. One is like the way we said M. So we said this is and this is positive, right? We call it the bending moment is positive. Then we said this and this is positive, right? These are the bending moment of shear forces. Moments and shear forces. But actual forces, if you consider this one, bending moment may be positive here. But actual force is negative, actual moment is negative. When you are writing here, is the actual force and moment we are talking about. So not to be confused with the like what is the shear force or what is bending moment there. You don't have to calculate it back. That what is the shear force there, what is the bending moment there. So if there is a confusion, we can also write differently. So let's say you call it M1, this is MM, this is VV, but here let's call corresponding to this one, we will call something else. Let's call this as P1, meaning that the force which is acting, this is P2, which is the force acting, right? And then this call it a small M1, right? M1, and then not this way, anti-clockwise. This is also anti-clockwise here. What we mean here is this VL multiplied by E at L. We are talking about M2. P2. We are talking about, and W at 0. We are talking about P1. If this is negative, you have to put negative there.
So we are taking those directions to be positive. According to that, we are converted
Yeah. M at L, you call it M2, and here M at 0, this is M1. Yeah, so this is the actual forces. Forces, you can just write and you just put the forces there, multiplied by those. Yeah. If you are writing bending moment, so accordingly you know that P1 equal to minus V and M will be minus M.
negative.
And hence you understand how. Always remember that when you are solving a elasticity problem, finally in your force vector, actual forces appear. You have to forget what is the bending moment there, what is the shear force. You are not doing anything. You are looking at that point, seeing what is the force there. So, so let us say you have a beam, node 1, node 2, node 3, and you have force like this, right? And like this. Okay, so and nothing else. Let's call it F1, let's call it M1, let's call it F2. Let's call it F3. Yeah? And they are the actual forces on the problem you are talking about. These are element number 1, this element number 2. The global force that you will write F1 is there. It will be positive or negative? Positive. Actual force you have to write, that's it. What about this M2? Positive because anti-clockwise. What about this? Yes. Your force vector is complete. They are forces only. Regardless of how you write here, finally it is the force that has to appear. Positive y direction, positive, anti-clockwise, positive. If otherwise, negative. Right there, that's it. You don't have to see how they multiply, how they translate into bending moment and all. This is just the mathematics. But the meaning is K times U equal to F, and F has its own sense. F has upward, positive, anti-clockwise, positive. That's it, nothing else. Yeah? Yeah?
So if we give WXP is integers.
We have what?
Left the term.
Leave the term.
Integration
Oh.
of WXP. If it was there, then.
Yeah. Okay, sure. So if you had some, if it's loaded, then it's different thing. Yeah. So plus you have to integrate 0 to L, and then your Px, Wx, P. This is also forces upward. So hence these forces are upward only defined. Yeah. So we any question, guys? Now we have to find out the stiffness matrix. What will we do? You have like this one. We also have Wx. We will also write in the same way. We need 1x multiplied by W1. Right? So let's call it W1 plus N2x, W2 N3x, W4 N4x. Yeah. we have the at least same expression for W as well, and you put the value here. Yeah. So you know that really means what? W0 is equal to W0 is equal to what? W1. WL is equal to, if you put WL, what happens? This L 0, this 0, this is 1, this is 0. So you have W3. Right? And dw over dx at x equal to L is equal to what? Is equal to W4. dw over dx x equal to 0 equal to. Yep. Hence you can put those values here, and you can write 0 to L dw over I d square uy over dx square dx. Just a minute, guys. Maybe urgent. Okay, that is equal to, now in one, sorry, here if you see, so WL, so that becomes a W3. So let's start from W1. So W0 we have times P, so we have W1 times E1, right, plus W2. W2 is what? This x equal M1, right? W1, W2 times M1. Similarly, plus W3 times P2 plus W4 times M2. Right? Those are the actual forces and moments at the end. Right? So this is how they appear. Okay. Now we will put these values there, and is all right? Plus integral, yes. Plus integral L dx. Okay, so we have this. Now we will put the values of uy and wx here. Yeah, so what will you get? We get 0 to L and double, we get double derivative of this. Yeah, so instead of writing like this, we can write straight away. Now that you are expert now, you can write here W1, W2, W3, W4. Then you have some value of K. Then you have U is equal to W1, W2, W3, W4, and then you have equal to F. Only thing is we have to find out what is the value of K, what is U. Yeah, so K is equal to K11, K12, K13, K14, and so on. This will be symmetric only. K23, K2, K22, K23, K24, K33, K34. Where you can find out the value, right? Where K I J equal to, we have done derivative, so both of them. So what we get equal to, we have EI there, we have more derivative of NI, it is x square multiplied by NI, d square NJ over ax square. Yep. Okay. So K is maybe like this. What is U? U is equal to, will be U y1 theta 1 U y2 theta 2 transpose of it. What about force? F is equal to, F, it will have two kinds of terms. One which will coming from here, so this will be P1, M1, P2, M2, and there will be another term which is coming from the distributed load. So you can write F by distributors, they write FP1, FP2, FP3, FP4. Where FPI is equal to 0 to L, the usual stuff, N I X Ex. Yeah. This is all because of this equation, right? This equation automatically, if you put these W and Uy, automatically you get this equation, this equation. You know that the sequence matrix here, U vector here equal to F. F will have two components, one coming from the reaction forces, N moments. There is N moments. The first one is N moments, and this is because of the distributed load. Yeah. Where U is given, that is, let's say it's fixed, theta is fixed, then you don't know the force, you will write R. So this is what it is. Actual integration, I did it on you. We have the answer already, right? You will get exactly the same way. Yeah. Do you believe me or don't believe me? Yeah? No? We'll take one example. One example means N1, what is the value of N1? You say 1 over Q, then you say x minus L square, and you say 2x plus L, right? Is correct?
Yes, sir.
So let's find out K11. Okay, so it's easy. We will first derivative of it becomes 1 over LQ, and then you will have 2 x minus L, 2x plus L plus 1 over L cube, x minus L square, and multiplied by 2. Right? Okay, now d square n1 dx square is equal to 1 over L cube. Then you have 2 2x plus L plus 2 over L cube
X minus L 2. 2 into x minus L.
2, just 2, no?
X minus L.
X minus L, yes. So x minus L multiplied by 2 plus 2 over L cube 2 x minus L. Right? Okay, so you get linear. So we will 1 over L cube, let's keep it in common. Then we have here 4x plus 12 plus 4x minus 12 plus 4x minus 4l. Right? Equal to
6 upon L cube.
so 4x 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 12x then minus 6l. Right? Okay, so that makes 6 over L cube 2x minus L. Fine? Okay, so square of it, so 0 to L, EI, and square of it. 36 over L to power 6, right? And then you have 2x minus L square. Okay, then you have dx. Okay, so equal to 36 I over L6. Then you have 2x minus L. So 2x minus L u of it divided by 3 divided by 2. L2 0. Six I L6 multiplied by 1 over 6 multiplied by
2x minus L.
so L cube
L cube.
minus
Plus.
becomes plus rather
Plus L cube.
L cube. Okay. So what is the value?
12 over L cube. Yeah.
12 I over. That's the answer.
Yes.
Now you believe me now? Yeah. Okay. Similarly, you can solve others. You can get exactly the same way. And same as what we have derived earlier. Right? Same value you get. So far we have just used the reckoning method to do it. You can also do the Rees method. Okay, so we take the 5 minutes. So the Rees method also you could have used, but for that you have formulation. We call it minimum potential energy formulation. And what do you mean by that? You remember, you say A is equal to strain energy, right? So you call strain energy, or rather, you say potential energy equal to strain energy minus work done. Right? Strain energy minus work done, or you say pi equal to psi strain energy minus W, right? So pi equal to and that has to minimize. So minimize or equal to minimum potential energy formulation. You minimize pi. What is strain energy? Strain energy is you write. So in case of beam, what happens? You have a beam, and then you have the stress. Yeah. So you say half E strain square, right, like this, right? And 4, so you write 0 to L, so whatever this strain means, right? So this strain energy, this is equal to, so strain is nothing but, strain is the x direction, sine xx, so half 0 to L E, and sine xx is given, right? You remember what is that? Minus y, you can see that d square dy over dx square. Yeah. So what you do here, this one you are multiplying, but since this is for the whole domain, basically you have to write the whole thing rather than write like this one. So that really means we have 0 to L as far as x is concerned, and then you have E, then this is strain energy, so y square d square dy over dx square. Yeah, and this actually for the whole area, right? Right? And this, yeah,
It is square.
area square. Whole volume, so dA multiplied by dx, this is like this, and hence this is what you get out of it is equal to half 0 to L E. Okay, take this out, so you get d square dy over dx square, the square of it, And then you have y squared dA. What is this guy? For the whole area of the cross section. Then we have 0 to L I d squared uy over dx square of it. Right? So we get this one, then W. Now W depends on the forces which are applied. Yeah. So if you have this force, just like let us say you have this is fixed here and fixed here, and then you have the P like this. This is the Px. Then W will be Wx will be equal to no not Wx W. Total work done is will be equal to Ex multiplied by Uy x. So total work done will be like that, right? So basically pi will be equal to half 0 to L pi d square uy over dx square dx minus that. Yeah. Minus 0 to L and dx dyx is equal to 0. Not 0, but minimize it. For this case, it will be like this. But let us say there is a force applied as well. So let us say something like this. You have the moment applied here. So accordingly, force will be whatever the moment is at this M at L multiplied by what is the theta at L. That will be also the work done. So hence, you have to subtract it and so on. Yeah, but this one is for this one. There at the end there is no moments, there is no force because of the moment, but there is a reaction force here, but displacement is 0, so work is 0. Only work done is because of the pressure, right? But this is also just to know that there is another. You do have the formulation for this also, and you can solve it. You can put the same n1 n2 n like y uy equal to as a function of n1 n2. You can put it there, and then you can solve. So that's the thing. You can solve it for the coefficients. Which are the coefficients? uy1, theta1, uy2, theta2. Those you are solving. Meaning that how you are going to solve? You are going to minimize it. And how will you do? Del pi over del uy1 is equal to 0. And you will solve for this, right? Similarly, del pi over del theta1 is equal to 0. Del pi over del u2 uy2 is equal to 0. Del pi over del theta2 is equal to 0. And they solve. You will have 4 equations, and then you solve, and you get the 4 coefficients, and that gives you the expression for uy. So this is how you do. we are done with the chapter. Yeah, so we just solve the problem. So tomorrow we will solve problem. On Wednesday also we solve problem. After that, I think there's no need to take classes. Anyway, we take plus 10 minutes every day, so that compensates. Yeah, so the idea is to give you also time to prepare. Yeah, so hopefully you will do good in the exam. Yeah.
What will the syllabus be for syllabus?
Syllabus will be full syllabus. See, really there is nothing called after the midterm exam. A lot of things we have studied before that will be applicable. So I don't want to say that yet. However, most of the questions will be from after the midterm exam. Yeah. Any question, guys? Those who are online?
Sir, I had a question related.
Yeah.
Are we allowed to use the PD toolbox?
PD what?
Toolbox. So that will convert MATLAB to something similar.
I'm not aware of what is that. PD toolbox.
So the PD toolbox will automatically discretize the geometry we import in MATLAB. And it also has a solution solver.
No, those you can use as a solving for as a comparison, because you have to use two things. One is programming, the other is you have to use some commercial software to compare. What we are talking about will be the one which I term it as commercial software.
So sir, we are supposed to code the whole solver.
Yes.
And all the discretization and everything.
Yes. Of course.
Sir, I am having trouble and discretization.
How?
Suppose there's a square,
Hmm.
rectangular geometry,
Okay.
and I want to discretize it into triangular elements.
Okay. So what's the
So, sir, rectangular geometry, every triangular element cannot be of the same size. It will be of different size, having some irregular patterns.
yeah? So what?
How will we locate the nodes inside?
You are saying this is a triangular element like this one, and then you have problem in.
I am discretizing in triangular elements.
Okay.
So, if I was supposed to use rectangular elements, it was simple. I would just divide the length and breadth.
So same logic you can do this side also. And see here, you have done like this, you just put like this. No, what's the deal? See, what's the issue, man? Tell me. See, and it is looking beautiful too.
So this is one way, but generally we see ANSYS. It uses mostly inside triangular elements are
You do this way, okay? Forget about the ANSYS. Okay, ANSYS have optimization. They will do such a way that it optimizes a lot of things, including the time. Even the node numbering will be such a way that inversion is faster. All those things are taken care of. You don't worry about that. Yeah? Got it? Do like this. That way you just have to do for just one, and then you can also repeat them. Yeah? It's up to you how you want to do it. Either you do this way, you can also do like this, and if you want, see. Even more beautiful. It's up to you how you want to do it. What's the problem?
It's in case of 3D elements, which have curves, 3D geometries with curves. I'll have to use a tetrahedron element 10 nodes. That discretizes something similar problems.
No, I think you are looking problems more than solutions. Don't look all those kind of things. I mean during my postdoc, in fact, I analyzed a bone rather than taking a section as this one. I took the section as this. and still I published a paper title, and it has a good citation. Okay, so don't give an excuse, just do it. It's fine. Okay.
No, sir, like I'm asking how will we do it?
This is supposed to be a bonus section. See, this is because from pixels I made a square elements and I solve it like this.
Mass generation, do we have to use any algorithm like left-hand method or quadrant method?
Don't use any algorithm. Just do it. Just simple method. Okay. What I have not taught, we are not supposed to do. Or if you do at your own risk. Yeah. That's not part of this course, guys. Here, you give me ku equal to f. Okay. And then you solve u equal to k inverse f. That you solve. All other things, I don't care. Given the problem, you should be able to get the weak formulation. From there, you get k equal to f form. You should be able to apply the boundary condition correctly. You should be able to solve the displacements, and you should be able to also find out the reaction forces. As long as you are doing that, I will be happy. Okay. I mean, those things are easy things you are talking about. Okay. Main thing is this. You solve this one, no? It's up to you how you discretize it. Yeah, and there is a way of doing it. So even if it is like this one, if you are taking very small elements, automatically everything takes care of it. Yeah. So that's the you don't have to exactly match. So if the circle, then exactly you have to match like this. Don't have to do like that. So it's okay that circular section, if you are matching like this, it's fine. It's okay. If you want to learn, if you want to exactly do like this, and you want to use higher order elements, do it. Right? So nobody is stopping you for doing it. You can use this kind of element to match this. Right? It's okay. Do it. You will also learn. But if you are not able to do it, you are facing difficulties because of that, you are not able to do project, then do the simple one. But do the project. You are giving me all excuse to not do the project. Yeah. Because it is, I'm not able to, match the geometry, hence it's difficult, so please don't ask me to submit the project. Is it? Whatever you learn in the class, just do it. That's okay. If you take the difficult problem, you will only learn. Right? So there is you can even have a difficult even if you're learning linear, you can even take non-linear one. All kind of things you can do. Newton adaptation, all those things you can apply. Okay. So for that you have to study also. Yeah. So you got it? Any other question, guys? Okay, guys. See you tomorrow. Yeah. Quiz.